All right. Well, thank you very much for inviting me here. I'm going to be presenting today about linear pricing mechanisms for markets without convexity. This is a paper with Paul Milgrom, and I'll get stuck right in. How do I advance?
Oh, click the right screen.
That one. OK. So the setting that we're considering is a quasilinear two-sided exchange economy. So there's going to be many commodities, L of them, plus money. Buyers are going to be indexed by N, and there's going to be N of them. And they all have quasi-linear preferences. That is, their utility is equal to a valuation over goods minus the payments they make. And we're going to assume natural things about these valuations, that they're bounded, non-decreasing, and normalized to be zero at zero. Sellers have usual profit functions, payments minus costs. Those costs are also bounded, non-decreasing, and normalized. But where we depart from the traditional general equilibrium literature is that we won't be assuming that the valuations are concave, nor that the cost functions are convex. So as a consequence, there may be no prices that lead to supply equaling demand. There may be no Walrasian equilibria. So the question is, what do we do in these settings? And the goal of this paper is to offer new extensions of the Walrasian mechanism that have many of the desirable properties of the Walrasian mechanism, but work well in these settings without convexity. And why do we want to study this question? Well, it's because non-convexities are fairly pervasive in our economy, and especially in some important sectors. So take, for example, the market for wholesale electricity generation. We all know there are huge startup costs associated with starting up a coal-fired power plant, for example. And what that means is it's just not viable to start up a coal-fired power plant for a small amount of electricity production. And so this is an example of a non-convexity in the cost functions of power producers. And similarly, this study was actually motivated by a market design in Australia by Martin Bickler and some of his colleagues in the fisheries industry, where there are large economies of scale. But generally, wherever we see these startup costs, switching costs, economies of scale, indivisibilities, complementarities, these are all signs that non-convexities may be a significant concern in these markets. And so we introduced two new families of mechanisms in this paper. Our first mechanisms are what we call the markup mechanisms. In these mechanisms, sellers are going to be facing a price vector P, and then there's going to be a markup, a positive real number alpha, such that buyers face a slightly higher price, 1 plus alpha times P. In this setting, we're then going to have an allocation to buyers and sellers, such that buyers are all allocated something in their demand sets given those prices. Sellers are all allocated something in their supply sets given those prices, and will enforce physical feasibility. So supply has to be weakly greater than demand, and budget feasibility also, so that there are more payments from buyers than there are from sellers. And the goal of these types of mechanisms is to work in markets with two-sided non-convexities, where we may not be able to guarantee that there are even exactly market-clearing feasible allocations. And so these allocations will typically have some unused supply at the end, and the role of the alpha, the markup in that setting, is to pay for that unused supply. In contrast, the second set of mechanisms, the rationing mechanisms, are going to be exactly balanced. So in these mechanisms, buyers and sellers are both going to face the same price vector, but the allocation itself may not be in the supply and demand sets of the various agents of that price. They may be rationed. That is, assigned something not preferred given the price. But we will choose the price and allocation so as to satisfy physical feasibility as before, and an exact budget balance condition. And so later on, I'm going to show you that mechanisms of this flavor exist and perform relatively well in large markets. But before I do that, I want to introduce our main piece of machinery for establishing our results, which is called the bound form first welfare theorem. It's a new version of the first welfare theorem for quasi-linear economies. And it all stems from the observation that if no Walrasian equilibrium exists, then any price and allocation pair must feature, by definition, one of two things. Either supply is going to be greater than demand for some goods, in which case there may be budget deficits, or demand is going to be greater than supply for some goods, in which case we're going to have to tell some buyers they can't have what they like given those prices. We will have to ration them. And it turns out that those two possibilities exactly characterize the inefficiency of an allocation. So we're going to measure inefficiency here using the usual surplus function, the sum of the buyer's values minus the seller's costs. the bound form first welfare theorem states that given any feasible allocation omega and any price vector, non-negative price vector p, we have that the welfare loss at allocation omega, so that's the difference between the efficient surplus and the allocation surplus, is no larger than the sum of the revenue deficit, so the budget deficit at the price allocation pair, and the rationing losses for buyers and sellers. So what do I mean by rationing losses? An agent's rationing loss we define as the difference between the maximum payoffs that an agent could get given a price. So you could ask a buyer, given the price that you're facing, what would be your best bundle and what would be your utility at that price, minus the profit they get at the allocation given the price. So we've given them a different allocation. So we subtract off the utility that they obtain at that allocation given those prices. So why do we call this a first welfare theorem? If you take a competitive equilibrium, a Walrasian equilibrium, it's a price allocation pair such that there is no revenue deficit and no agents are rationed. So that says that there is no welfare loss as a consequence of rationing. That allocation is efficient. Okay, so I'm not going to present the proof of this result, although it follows fairly simply from weak duality in the convex program. So instead, I'll explain to you how we use these results. So our first results are about the markup mechanisms. And we're going to make some assumptions. We're going to be looking at these mechanisms in large markets in which the number of buyers is growing to infinity and the number of sellers. We're going to assume that the non-convexities are bounded as the market gets larger. In other words, the demand and supply sets, which may be non-convex in this setting, any holes in them have a bounded radius. We'll assume that there are growing gains from trade. The efficient surplus grows at least linearly in n. And there's a technical assumption about the set of approximately clearing prices, but you can look at that in the paper. So our result is that there exists a markup mechanism such that this markup parameter is of order 1 on n. So as the market gets large, these markups needn't be very large. And moreover, this markup mechanism is nearly efficient. So the proportion of the surplus lost in this mechanism compared to the efficient allocation is also order 1 on n. And it's nearly incentive compatible. Well, in particular, it has exactly the same incentive properties as the Walrasian mechanism. And I'll explain this later, but under an assumption called strong monotonicity, the maximum gain to any misreport is in both the Walrasian mechanism and this instance of the markup mechanism is of order 1 on n. Finally, this mechanism is easy to compute in some sense. In particular, it only requires convex optimization problems to solve conditional on any alpha, and then we'll perform a bisection search over alpha. So really, the only hard part of convex is that bisection search. Okay, so let me give you an idea of how we find this mechanism. So start off with, we'll just fix an alpha. All we do is sort of the natural things you would do. We convexify the economy. We take the convex relaxation of the efficient allocation program. And the somewhat novel step, I guess, is that we scale down the buyer's valuations by a factor of 1 plus alpha. The idea here is that if you're willing to buy an allocation at a price given this valuation function, then you'll be willing to buy at the original valuations at the price p times 1 plus alpha. And the last component we add is an additional auctioneer demand for each good. I'm going to explain the role of that in a minute. But it depends on the number of it's equal to delta L. That must be cut off on the slide, but depends on the radius of non-convexity. And so then we find, using a convex program, the Walrasian equilibrium in this economy. The next step is to round the allocations using a sort of classical result that some of you may know called the Shapley-Folkman theorem. So the idea of the Shapley-Folkman theorem in this setting, the easiest way to explain it is that given any Walrasian equilibrium of the convex relaxed program, there exists a feasible allocation, okay, which is in the demand and supply sets at the given price and is nearby the relaxed program solution. So the problem with the allocation we obtained in the first step is that it may have been infeasible for some buyers. Now we ensure that it's feasible for all agents, and moreover, it's demanded and supplied given those prices. Okay, so the final step, sorry, I'm going to go back one step. And here we see the role of the auctioneer's demand. Okay, so if we hadn't included that auctioneer's demand there, the Shapley-Folkman theorem only guarantees that we can move some distance from the relaxed program's allocation, but it may be that we require more, that when we move to the feasible allocation, that requires more units of supply. But we've already guaranteed there, in this step, there was sufficient supply to carry any additional demand.
Naive question, so what's the Shapley-Folkman theorem?
Yeah, so this is the application of the Shapley-Folkman theorem to the Walrasian equilibrium setting, which is where it actually comes from originally. But the Shapley-Folkman theorem itself just says if you take any sets, a family of sets Sn, and take the Minkowski sum of them, then the distance between, the least distance between a point in the Minkowski sum and the convex hull of the Minkowski sum is no more than some delta L. Yeah. Okay, so the final step is to find a good alpha. Well, the only role of the alpha here is to ensure that the mechanism is budget balanced. So all we're going to do is search over alpha to find the least alpha such that budgets do balance. Okay? And it turns out that this is of order 1 on n exactly because the wasted supply is bounded above by this delta L times 2. And so we're basically paying for one buyer's worth of demand using this alpha. So that this markup, this tax, is going to get smaller as the economy gets large. So that's the construction of this markup mechanism. To see that it's approximately efficient, we apply the bound form first welfare theorem. And so remember, the bound form first welfare theorem used a single price and allocation. Well, we'll just pick one of the prices and calculate the bound given by the bound form first welfare theorem at that price. So let's just choose the seller's price. By construction, each seller is getting something in their supply set. They're not rationed, so their rationing losses are 0. By construction, each buyer is getting something in their demand set at the price 1 plus alpha times p. And because alpha is small, it turns out via the envelope theorem that their rationing losses then are also small. That's the difference in the valuation functions. They're also order 1 on n. And since there are n buyers, that's a constant as the market grows large. And finally, the budget deficit's also constant, leading to a constant total loss. Okay. The last piece of the puzzle is the incentives, and I'll talk about this really quickly. We make an additional assumption here called strong monotonicity. So the idea of strong monotonicity, the simplest way to state it is in an economy with just one good. As long as the demand the slope of the demand curve is bounded away from 0, we'll say that demand curve is strongly monotone. In particular, the slope is bounded by some constant that's away from 0. It turns out, and I show this in another paper, that both the Walrasian mechanism and the markup mechanisms are ex post order 1 on n incentive compatible, and exactly in the case where the demand function of each agent is strongly monotone. Now, this is a big assumption, but it turns out this also works just for expected demand as well. So if the expected demand correspondence is strongly monotone, then we get this ex post incentive compatibility with high probability. So I can refer you to my other paper on this, but it turns out that the markup mechanism then has exactly the same incentive properties as the original Walrasian mechanism. Just jumping forward to the rationing mechanism, I'm just going to state the theorem on this one and not talk through the proof. But the idea of the rationing mechanism, you'll remember we are going to assume that one side of the market has convex preferences for the rationing mechanism so that we can definitely get a market clearing allocation. And moreover, we're actually going to assume that one side of the market has strongly monotone preferences. Okay, and that's going to give us this result, that there exists a rationing mechanism which is nearly efficient and at an order of magnitude faster than the previous result. Here, the total surplus lost relative to the efficient allocation is of order 1 on n. So here the loss gets small very quickly. Again, it has the same incentive properties, and it's even simpler to compute using just 2 convex optimizations. Okay, so with that, I'm just going to conclude. So we introduced a new version of the first welfare theorem that works in quasilinear economies, and it allowed us to produce 2 new classes of mechanisms that we think work well in non-convex markets. And these mechanisms have many of the similar properties to the well-rationed mechanism. They're not exactly efficient, but they're approximately efficient. They have the same incentives, they're individually rational, relatively easy to compute. They use linear prices, and they have no budget deficits. And so, yeah, that's, I think, all I have to present, but happy to take questions. Thanks.
So maybe there's something just a little puzzled why you can do these original theorems. Is that the strong monotonicity? Somehow I don't see how, if I add you to your system 1 million buyers and sellers who don't have any value or any goods, that's not going to help you. So how are you avoiding this?
Are you talking for the incentives results, no, for the rationing? The rationing. The rationing mechanism as well. What it is actually is our without this strong monotonicity type assumption, even small distances in allocation space can translate to really large distances in utility space. And so what we have here is that the total allocations are going to be close. And if there's rationing, then there's going to be a shadow price for all of the agents that might be a little bit, some distance from the price that we're going to use in the rationing mechanism to determine payments. And since these prices are not exactly equal, without some strong monotonicity condition, we just don't have a bound on the utility difference. Yeah, I'm happy to talk more about it, but the dual of the efficient allocation problem could be very flat. Yeah. Yeah.
Where do you use the assumption of a large market?
Well, only because in the first results, in the first set of results, just because in fact it may be that we need large markets for this not to choose a trivial zero trade allocation, because there is the chance that by construction there may be excess unused supply in these mechanisms, and in order for us to be able to find a markup so that the total payments cover that excess supply, the cost of that excess supply to the suppliers, then it may need a large market. Yeah. Cool. All right. Thanks.